Hello, my name is Akir Albadan, and this is my lab number 4 circuits lab video. So to introduce you to the lab, the description and purpose, well, we want to predict the behavior of ideal RC circuits using physics principles of conservation of energy, like Kirchhoff's laws, and Ohm's law using an online simulation, which we used PhET. Some fundamentals, Kirchhoff's circuit laws, we have the node rule, which states that the current in equals to the current out, and then we have the loop rule, which says that delta V around a loop is equal to 0. We also have Ohm's law, which is V equals to I times R, and we also have concepts about resistors and capacitors in series and parallel, or how to reduce circuits. Another key concept is capacitance, and also the time dependence in RC circuits, and how this is the linearized version on the right over here. So the introduction continued. All measured values match predictions using physics principles and formulas. We had an initial current of 0.02 amps and R times C equals 6 seconds. And an exponential relationship between voltage difference and time can be established as the formula suggests. So assumptions and model, we used PhET again, and the assumptions was that the resistance of essentially everything apart from the resistors is negligible. So for all parts, the system was the circuit, and there weren't any surroundings. So for part one, the main concept here was that the current before the resistor is equal to the current after the resistor. And we were able to solve this by finding equivalent resistance using using resistors in series formula. We had an actual reading of 0.02 amps, which matched the calculated value. And after replacing one amp meter with a voltmeter, there is no current, and delta V is 3 volts. That's because the circuit's not closed. So there's a potential difference across the wire break. So experiment and observations continued. Here on the left, you see the delta V values listed across various segments. And what's important to note is that the sum of delta V is equal to 0 around the entire loop. And that matches the observed readings. And the ammeter reading does not change because the voltmeters have a very high resistivity. And our reading was 0.02 amps. And here at the bottom right, we have a graph that matches the values listed on the left. So we have a decrease from C to D, another decrease from E to F. So for the second part, we connected the ammeter in parallel with 100 ohm resistors, and the current reading increased to 0.06 amps. And then we have some calculations from part 5 and 6, and those resistance values calculated using the voltage readings are slightly higher than expected, but generally accurate, and maybe due to a low accuracy voltmeter even within the simulation software. So part 2, we set up with a 10 ohm bulb, a 20 ohm bulb, a 200 millifarad capacitor, and 9 volt battery. So when the battery and capacitor are connected in series, the light decreases in brightness until it's no longer producing light. And then the capacitor is charging, the current in the circuit is decreasing. When the capacitor is discharging, the current in the circuit is also decreasing. So for the 10 ohm bulb, 10.5 seconds charging, 12.4 seconds discharging. 20 ohm bulb, 17.3 seconds charging, 22.3 seconds discharging. And then for part 3, we set up a 9 volt same setup as before. And then we plotted 20 seconds by using just a normal stop clock. And we have the linearized version. And from here, we were able to show that that this is the line equation that we would have. So we would set -1 over RC equal to this value, negative 0.1671. And we got an RC value of 5.98. And the expected RC is 6.00, so it was a bit off, but still fairly accurate. So model discrepancies, we shouldn't have any because the computer model is ideal. All assumptions mentioned in previously on slide 4 about resistivity are met. And sources of error, well, we could have some human error, as I might have not stopped the timer at the exact same time, throwing off some of the readings. So what if we used a real amp meter? So a real amp meter would have a lower measured values for current because the meter itself has some resistance. The real amp meter may also have a lower degree of accuracy. So what if we used a real battery to charge the capacitor? Well, our model would predict the capacitor to fully charge instantaneously because there'd be no resistance, but in real life, the wires have resistance, so it would take some amount of time for the capacitor to charge. Thank you for listening to my presentation.